तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, last class we were looking at how, given a particular circuit, we can go down to the I squared L layout. We shall continue with that. So, last class we had taken up the circuit based on NOR gates, and it was the well known half adder circuit, where I will just draw the circuit again, and shall just go ahead. So, this was the circuit. Okay. So, what we said was, when we want to realize it using I squared L circuit, the way to do it is first to go down to the transistor level. That is, first to do that we have to number these gates. Okay. And each gate, all right, is represented by a node at the I squared the transistor level. Okay. Each gate output is represented by a node, and the number of transistors or the number of collectors which are connected to the node represents the number of inputs to that NOR gate. Okay. And the number of fan outs of that particular gate is actually reflected in the number of collectors of the subsequent transistor, okay, or the next transistor. So, the circuit, transistor level circuit which we had drawn is something like this. Okay. So, these are the two inputs A and B, all right. So, you join them together. Okay, this is gate 1. So, gate 1 has inputs A and B. Okay, these are the inputs, all right. So, this is gate 1. Then inverter, all right, there is an inverter here. So, gate 2, okay, this is just, this node has just one collector connected to it, okay, that is, it is an inverter. So, one input, okay. And similarly there is gate 3 which is also an inverter, and then gate 4, the inputs are the outputs of 2 and 3. So, these are at the bases of these transistors, okay. The NOR gate configuration, you remember, is from base to base. Okay. So, this is the output of gate 4, the NOR gate, the inputs are at 2 and 3, the outputs of gates 2 and 3, this is the output 4. And then gate 5, the inputs are from the output of gate 1 and the output of gate 4. So, from these points, these are the input points to that gate, all right. So, you have one more transistor here, all right, and one more transistor here, and so when you join the collectors together you get another NOR gate, okay. And so, this is gate 5, okay. If you want, you can take the output, okay. If you want sort of TTL levels, okay, you can connect a resistance like this, VCC, okay. You can take it out, okay. That means this voltage here is going to be either 0.2 volts or 5 volts, okay, which corresponds to TTL levels, all right. So, that means what I mean is TTL level is somewhat considered a standard, okay, that is, from this output you can feed it directly to a TTL gate maybe, okay. So, internally, as we said, the I squared L, the voltage levels at each node just changes from 0.2 to 0.7 or 0.8 volts maximum, okay. And whereas if you want to take it out, okay, for the external connection, you would like to have proper levels, voltage levels, and you can do that this way, okay. Now, if you want to realize this, okay, fabricate this, what you require is a layout, okay, for someone to fabricate it, then the mask layout. So once you have the mask layout, it can be fabricated, because the mask layout gives you the different regions where you want to diffuse differently, okay, that is P diffusion, N diffusion, base diffusion or collector diffusion, the metal contacts, etc. So how do you go to the mask layout? Okay, if you recall the layout of an I squared L cell, it is basically the same thing, but now you have so many different cells. Okay, so you have 6 transistors, so you will have 6 cells. Okay. I would just like to say here that in this circuit, of course, we have not drawn the PNP transistors, but it is assumed that at each base you have a PNP transistor. Sometimes we forget to draw it, okay, because it is assumed that it is always there. All right, that at every base of an NPN you have a PNP. Okay, because it is not so important in the sense from the circuit point of view, because it is only how you connect the NPNs that gives you the circuit. Okay, the PNP is always connected in the same fashion. All right. Okay, so coming back to the layout, okay, I think we had started on this in the last class. Okay, so this is the injector rail, okay, and on either side of that you have the transistors. Okay, so the first transistor, okay, if you call this transistor 1, okay, you can call this transistor 1. Okay, I think it's going to be confusing, but anyway, this is already 1, 2, 3, 4 on the board. So anyway, if you consider this to be the first transistor, okay, at the base of which you have the input A, okay, this has 2 collectors. All right, this particular transistor has 2 collectors. So collectors, you know, are drawn like this, the layout. Then this is the contact for the collectors. So this is one cell. All right, one base, 2 collectors. Okay, then similarly you have another transistor whose base is, at the base you have input B, okay, and you again have 2 collectors. Okay, so I can draw it like this. Okay, so these are the 2 collectors, and this is the base input, and you have the input B here. Okay. Now, the one of the collectors of these 2 transistors is shorted. Okay, they are shorted to give you the first gate, NOR gate. Okay, and that output goes to the base of another transistor. So what you can do is you can have another transistor like this. Okay, the base input is like this. Okay, and there is just one collector for that transistor. This transistor is one collector. Okay, so these 2 collectors can be shorted. So this is the metal line running. Okay, and these 2 collectors are shorted. Okay, and this goes to the base. So this is the base of one transistor here. Okay, all right. Now again, we come to these transistors now. So the other collector of these transistors, okay, goes to the base of 2 other transistors. Okay, so I can draw them like this. Okay, and these transistors have just one collector. Okay, so one base and one collector. Okay, and there is one more with one base and one collector. So the other collector of this transistor goes to the base here. The other collector goes to the base here. Okay, and then so for these transistors again the collectors are shorted. Okay, and it goes to the base of another transistor. So there is, and this transistor also has just one collector. So these collectors would be shorted and going to the base. So I draw the base this side and the collector here. Okay, so these collectors are shorted and goes to the base here. Okay. All right. So we have realize this. Now what is left is these two transistors, the collectors would again be shorted, okay, and so basically we have to short this, okay, and the output we get is from this point, all right. So this is the point, is the output, all right. Now all these transistors, for all these transistors, this is the common injector, okay. So this requires an injector contact here, where we feed the common injector, okay, all right. See, all these transistors, the injector point is common, all right. You have a PNP transistor at each of these bases, okay. In fact, you can consider them to be a common this is a PNP transistor, this base is grounded, okay. This is a common this is actually a multi collector transistor this way, okay, this PNP, okay. So all this goes one here, one goes here, so you know, all right. So if you have 6, you know, this, so this is a common point actually where you are feeding the power supply, okay, all right. So this is a common PNP, one emitter. So basically you see you have a PNP, okay, PNP. So this is okay, the common, the cell consists of a PNP and an NPN, okay. So the NPN is of course going down, so this is the PNP, all right, okay. This is the common injector point, okay. So you require a connection here, and of course finally you also require the guard ring which will go round, okay, maybe it goes round like this, so this is the N plus diffusion which acts as a guard ring, okay, and you can have a common guard ring for the entire structure, okay. So these are the two inputs, okay, these are the two inputs you have. This is the output, actually the sum output, okay, and this is the injector input which gives the input current to the system, all right. So and you have the different regions, okay. So this is the guard ring, I think, which goes round all over the all around the circuit. I can draw it like this, okay. This is the injector, common injector diffusion, okay, gives the PNP transistors. These are the individual base diffusions for the individual cells, in which you have the collector diffusion. So these are all the collector diffusions which are done simultaneously, and then you have the contacts. So one contact you take from the base, the collector, and this is from the injector. So so these are the different mask levels, all right. So you see that the economy in the layout is very striking, in the sense that you have achieved, what you have achieved using this, you know, is one full adder, sorry, a half adder, okay, and you just require 6 transistors, and the layout area is going to be very, very less compared to any other technology, okay. So that is the big advantage of I squared L, okay. So it is very much suited for large scale integration. Okay, is this clear? How we go from the circuit, from the gate level circuit, okay, to the transistor level, okay, is very easy once you know the rules, and from here to the layout. So once you have the layout, you can give it to any process engineer, okay, he can start making the masks and the fabrication, okay, and you get the circuit, all right. Okay. So this is about a NOR circuit, okay. We shall also look at this, as we said, we have already studied that the I squared L can be configured as both as a NOR gate as well as a NAND gate. And the NOR, you remember, it's from base to base, and as for the NAND it is from collector to collector, okay. I think let me remove this, I think. Okay. So we shall go on to a NAND circuit. a slightly more complicated looking circuit, but well, it's not so complicated anyway. Well, this is the circuit of a positive edge triggered D flip flop. Okay. So it has 6 NAND gates. Okay. So this is the D input. Okay, and this goes here. This goes here. We have one. Okay, the clock input is here. Okay, and then you have one line coming here. From here, one line comes here. Then you have the latch at the output. Okay, so this is D, this is actually Q bar, and this is key. Okay, so this is the positive edge trigger D flip flop. I need not go into how it works. You can do that yourself, I believe. Basically, what we are trying to do is see from this given circuit. This is a circuit. Okay, how we again can go back to or realize it using I squared L. Okay, so again we have to frame the rules for NAND circuit. Okay, how to do it? Okay, to draw the transistor level circuit. Okay, again we do it the same way. Start with the same way. Assign a number to each gate. This always helps. Okay. So 1, 2, say 3, 4, 5, 6. Okay. Now this is a NAND circuit. So you remember it's from collector to collector. So each gate output is represented by a collector of a transistor. Okay, and multiple outputs is represented by multiple collectors. That is, basically, if you have 2 outputs, no, from each gate. For example, here it is one going here, so it's fan out of 2. Okay, one going this side, one going that side. So this particular transistor, which represents gate 4, okay, must have 2 collectors. All right. So multiple outputs is represented by multiple collectors, and again the number of inputs to the gate is represented by the number of collectors connected at the base. So the number of inputs to the gate is represented by the number of collectors connected at the base. Okay, so these are the rules, set of rules which we follow. Okay, similar to the one for the NOR gate. Now once we do that, we can realize this using transistors, okay, in the I squared L configuration. So again, here I'll just draw the transistors first. Okay. So you have 6 gates and you have 6 transistors. So 1, 2, these are the numbers 3, 4, 5, 6. Okay. Gate number 1 has a fan out of 2. Okay. So, this is going to have 2 collectors. I can just draw it straight away. Okay. 2 has just one connection. Okay. So, it is just one collector. Okay. 4 has 2 fan out of 2. Okay. So, it has 2 collectors. 3 has fan out of 3. So, 3 collectors. Okay. 6 is fan out of, well, if you take 1 out, okay, it is 2. Okay. So, and 5 is fan out of 2 again. So, all right. Now, you make the connections. So, 1 is coming here. So, this is the D input. Okay. From here, you have one connection to this point. All right. Okay. From here, from the output of 1, okay, one input goes to the input of 2. Okay. And the other output of 1 goes to the base of 4. Okay, as input to gate 4. Okay. So, and then from the, okay, then 2 goes to the base of 3. Okay. And from the output of 3, there are 3 outputs. 1 is going to the input of 6. Okay, I think just to help my drawing, I take it from this collector. Then 1 goes to the base of 2 here. Okay, and another one goes to the base of 4 here. Okay, all right. And from 4, one of them is gone there, one goes to 5. Okay. From 5, one of the collector goes to the base of 6. From 6, one of the collectors goes to the base of 5. Okay. So, these are the remaining collectors. And then you have the clock, sorry, the clock. Okay. So, I have one going to the base of 4 and the other going to the base of 3. You must remember here that in I squared L, okay, in the NAND configuration, okay, each of these inputs, okay, is actually the collector of a transistor. Okay, all right, is coming from the collector of a transistor. Okay. And then it is very important to note that you cannot have, although in the circuit, if you look at the circuit here, you know, you have one clock in, we have drawn one clock input like this, and it goes to the one goes to 4 and one goes to 3. Okay. Here I have drawn 2 clock inputs. Okay. I did not draw one clock line going here and here, okay, because they must be separate. Okay. They are 2 collectors of one transistor from a multiple collector transistor. If I had just shorted this, okay, I would have shorted, say, the input of 3 and input of 4, okay, which is not allowed. So, again, just to you must remember that why we use multiple collector transistors in I squared L. So, these 2 collector input, this clock inputs, okay, they must be separate and they must come from the 2 collectors of some transistor, all right, okay, where you are generating the clock. So, you cannot have one clock point going to all of them, because you will be shorting all these lines in that case. Okay. So, you must have in this case 2 clock inputs going to the 2 bases. Okay. And now you can just check or verify with the rules, okay, going back to the circuit. So, if you take each gate, gate 1, it has 2 collectors, and at the base there are 2 points, 2 nodes. Okay. At the nodes you have 2 inputs. So, if you look at gate 1, there are 2 fan out of 2 and it is a 2 input NAND gate. Okay. Similarly, if you go to gate 4, it has 3 inputs and a fan out of 2. So, at this point, okay, you have at this node you have 3 inputs, okay, and 2 collectors. Okay. Similarly, for all of them, so gate 3 it has 3 collectors, okay, and there are just 2 inputs. Okay. So, it is a 2 input NAND gate with the fan out of 3. So, if you look here, okay, it is gate 3, it is a 2 input NAND gate with a fan out of 3. Okay. So, you can check, verify. It is very important to verify. So, it must satisfy the rules which we have laid down. Okay. Once you do that, the next step is of course layout. Okay. And I think I do not want to waste the time here doing the layout. I think you can try it out yourself. Okay. So, with an injector, okay, you can have, again as we did for the NOR gate, okay, once you have the transistor level circuit, it is very similar. Okay. All right, you have to draw the individual transistors, okay, and make the connections. Okay. So, I leave it to you as an exercise. Okay. I think you should be able to do it. All right. Okay. So, we have seen how you do the layout, okay, for a NOR case as well as a NAND case. Okay. I will just give one more example of another circuit, an interesting circuit which is realized very easily using I squared L. Okay. So, I just remove this. Okay. I think you should be able to. Okay. So, the circuit I was talking of is a decoder. Okay. I think you know what is a decoder. Okay. Say a very simple, say 2 into 4 decoder. Okay. It is going to have 2 into 4 decoder. So, it has 2 inputs, okay, and 4 outputs. Okay. And you know that if there are n inputs, you will have 2 to the power n outputs. Okay. So, suppose I call these inputs A, B. Okay. The outputs here are, you know, you can write them as NOR gates. Okay. A plus B bar. So, all the 4 possible combinations. Okay. So, all the 4 combinations, and this is very easily realized in I squared L. Okay. So, you require, I will just draw the transistor level circuit. You have A, you have the 2 inputs A and B. Okay. So, you have to realize the complements also. Okay. So, here you have A bar, here you have B bar. Okay. And now, so if you want to realize all those combinations, okay, if you take this and join them here, okay, you have the NOR of A and B. Okay. If you take the collector of this and join them together, so here you have A and B bar, here you have A bar and B bar, the NOR of these two. Okay. If you want to realize the other two, okay, you have to take one more collector here. Okay. So, this is going to give you the NOR of A and B bar if you want. You have to join this together here. Okay. And if you want the NOR of B and A bar, okay, you have to take the collector of this and join them together. So, you see that basically you require 4 transistors, okay, and you can just join the collectors and you can get a 2 into 4 decoder. Okay. If you have a 3 into 8 decoder, you basically require 6 transistors. Okay. A, B, C, you have to just generate A bar, B bar, C bar, okay, 3 more 6 transistors, and you have to just tie the collectors together properly. If you require a 4 into 16 decoder, you just require 8 transistors. So, you see that it is very economical. Okay. I mean, you require very few transistors, okay, compared to any other way of realizing. Okay. So, this is another way, and the layout, okay, usually one way to do it is especially for the decoder, you require 4 transistors. Okay. So, how you do it is, you have the 4 transistors like this. Okay. The injectors, okay, are usually done this way. So these are the injectors in between. Okay. Now, in these transistors, suppose you have the A input here, okay, and the B input here. This is the base of this transistor, okay, and you have one of the collectors, okay. So this collector here of this. So if you have A, you have B, okay. This goes as base input here to this transistor, all right, and again one of the collectors here, okay, goes in as base input here, all right. So that is what we are doing. One of the collectors goes in as base input to the other transistor, all right, okay. So for this transistor, one of the collector goes as base input here. So this transistor has a input A, okay. So it goes here. This transistor has an input B. One of the collectors goes as base input there. So this transistor has a base input A. One of the collector goes as base input to this transistor, okay, this transistor, okay, B. Now what you do is, so one collector here A, this is one collector, okay. I hope I have space to draw, okay. So this transistor one collector, okay, and this transistor one collector, okay, you can just short them, okay, all right. You get the NOR of A and B, okay. Now this collector of this transistor, okay, and one collector of this transistor, if you short that, you get the NOR of A bar and B bar, okay. Now if you take one from here collector, okay, and this is A and say B bar, okay, okay, and this is a metal line running all over, shorting this and this, okay, you get A plus B bar, okay. The other one, okay, you take one from here, this one collector, okay, and from here, so you get the NOR of A bar and B. So you have the all the 4 combinations, okay, all right. The injectors, okay, these are the injectors, okay, this is the one injector here, one injector contact here, one injector contact here, okay, you can short them, all of them together, and this is the injector. So basically what we have done is, these are the injectors, okay. The injector that is of the PNP transistor. So this is the PNP. So the injectors are injecting holes into the base of the NPN transistors, okay. So they are positioned in between the 2 transistors, okay. This is done in case the number of collectors, you know, of the NPN becomes quite large, okay, then it is necessary to have this type of structure, because if you have the other type of structure, okay, this type of structure, you know, this is the injector and you have this type of structure, and if the number of this, suppose this is the base contact and you have number of collectors, okay, all right. So we shall come to that in more detail later on. So if for this collector, okay, this injector is very far away, okay. So what it results in is a lot of series resistance comes into play, and that is going to hamper the operation of the device, okay. So if there are too many collectors, okay, it is better to have this type of design, okay, where the injector is facing, all right. So each of these collectors, okay, is actually not very far away from the injector. All right, that is they are parallel. The injector rail is parallel to the base diffusion. Of course, for 2 into 4 decoder you might as well have this design, but why I drew this is because if you go for 3 into 8 or 4 into 16, okay, it's very simple, you know, you just have the same type of layout. Okay, if it's 3 into 8, okay, you will have 2 more of these, the C input, okay, and again you will have, instead of 4 lines running like this, you will have 8 lines running, and you just have to place the collectors in the proper position. Okay, you make the layout in such a way that you have the collectors in the proper position, and you can connect them by metal lines running straight like this. Okay, so you can have 3 into 8, 4 into 16. Okay, so 4 into 16 means you'll have just 8 transistors like this. Okay, and in between you have 7 injector rails. Okay, and you short them, the injector rails, with a common contact. Okay, and you have the outputs running like this, straight lines, where you short the corresponding collectors. Okay, so it gives a very beautiful design. Okay, so this is how you can design decoder, I squared L decoder. Okay, and it is very convenient. Okay, all right. So this is about the layout. Okay, so we have seen how, given a circuit, okay, all right, you can go back to the transistor level circuit for the I squared L, okay, and then do the layout. Okay, the layout is basically for a designer. Okay, the layout is the final output, okay, which can be passed on to the process engineer to actually fabricate. Okay, so that we come to this section now of the discussion on I squared L. Okay, and the next issues which we will be looking at in I squared L is some other points. Okay, all right. Now, so the next issue which we should be looking at, so we have seen how we can realize the circuit, but again another important point remains to be addressed is that given a circuit, okay, I shall again draw the I squared L cell. Okay, given this circuit, more from a process point of view, okay, how do you ensure that this circuit is going to work? Okay, all right, that is, one has to ensure, that is the design from a process designer's point of view, that is, we have to ensure that this transistor, the NPN transistor, actually goes to saturation. That is very important in I squared L, okay, because the voltage levels are such, you know, this has to go down to 0.2 volts, otherwise you cannot switch off the next transistor. Okay, all right, so this has to go to saturation. Okay, so how do you ensure that this transistor goes to saturation? Okay, you have, of course, this is going to some base, so you have another PNP here. Okay, all of them, all the collectors will have some PNP. Okay, at the base. Okay, now if this input is high, okay, or you have a cutoff transistor basically here, then what happens is this the collector current of the PNP goes in as base current, and this transistor, and this base current must be sufficient to drive this transistor to saturation. Okay. Now, if you assume very simplistically, let us say that all these current sources are same. Okay, this is I naught, this is I naught, this is I naught. Okay. Now, the condition for saturation, you know, is that beta IB must be greater than IC. Okay, all right, whatever is IC. Okay, if this condition is satisfied, then the transistor goes to saturation. Okay, all right. Now, so in this case, okay, the total IC is equal to n times I naught. So, if you assume that each of them is I naught, so and the base current is again I naught. Okay. So, beta I naught must be greater than n times I naught. Okay. That is, beta must be greater than n. So, beta of the NPN transistor, if it is greater than n, that is the number of collectors, then the transistor goes to saturation. Okay. But this is very simplistic, because of the fact that when this transistor goes to saturation, okay, the base voltage is around 0.7 volts or so. So, this is high. Okay. So, what is the condition of this transistor, this PNP transistor? So, the base voltage is high, base emitter drop is high, as well as the collector to base voltage. Okay. So, this transistor is in saturation, in fact deep in saturation. So, this transistor, when the transistor goes to saturation, you know the effective beta of the transistor is quite low. Okay. So, this is not behaving as a good current source. Okay. That is, the collector current will not be the same as the emitter current for this one. Okay. Whereas, for these transistors, since this voltage is low, okay, so this is going to have larger current. Okay. So, basically the base current is depleted because this transistor is in saturation, whereas this current is high. Okay. Because this transistor is in the active region, collector base is around 0.2 volts, okay, whereas base emitter may be 0.7 or 0.8 volts, okay, which means VCE, okay, is sufficiently large, and you have the transistors in the active region. Okay. So, these I naughts are obviously not equal. Okay. So, we have to find out a condition, okay, to for the transistors, for this circuit to work. Okay. That is, the condition for the transistor to go to saturation, okay, in terms of the transistor device parameters. Okay. So, that is what we are going to take up next. Okay. So, that gives us an input into the design of the transistor as such. Okay. So, I suppose you understood the problem. Now, we have to look at the solution. Okay. For that, what we are going to do is the transistor equivalent circuit which we are going to use is again the Ebers-Moll circuit model, okay, which we are familiar. So, I will just draw that model. Okay. So, you have three current sources. So, this is the base point, this is the collector point, this is the emitter point. Okay. So, what is this current source equal to? Is exponential Vb by Vt minus exponential Vbc by Vt. Okay. This one is Is by beta f exponential Vb by Vt minus 1. Okay. And this one is Is by beta r exponential Vbc by Vt minus 1. Okay. So, this is the Ebers-Moll model which we have already derived, okay, in the first few classes. Okay. So, we are familiar with, so we can take it up straight away. Okay. Now, for the again going back to the condition for saturation of the I squared L cell of the NPN transistor in the I squared L cell in terms of these parameters. Okay. Now, all right. So, again the condition for saturation is condition for saturation is beta IB must be greater than IC. All right. Okay. Now, if I assume, okay, in that I squared L cell, you see just a bit it is a bit confusing because this is a multi collector transistor. okay, then what is the value of Is or whatever we are going to take for this. What we will assume is that a multi-collector transistor is basically of, say, consisting of n collectors, is usually consists of n transistors in parallel. That is, the base emitters are parallel. Okay, there are n transistors. Okay, the base emitters are in parallel, and you have separate collectors. Okay, so there are n individual transistors, say. Okay, and each transistors you have an Is, that is saturation current, at beta, etc. All right. Okay, so if you do that, for these transistors, what you have is beta f. So you have IB. What is IB equal to? There are n transistors, okay, n times this IB is given by Is by beta f exponential Vb by Vt minus 1, okay, and so for that transistor, okay, Vbe, and of course you have another term Vbc by Vt. Okay. Now we shall assume that Vbc, because these exponential terms, you know, if this is even when Vc is 0.2, suppose this is 0.7, Vb is 0.7 and Vbc is 0.5, okay, because they are exponential terms, exponential 0.7 by Vt is going to be much greater than exponential 0.5 by Vt, okay, all right. So we shall assume that this is mostly given by this Vbe term, okay. So we can write n times Is by beta f, okay, exponential Vb by Vt. Again we neglect minus 1, which is much smaller than that, is greater than Ic, which is again n times, we can, I will write I naught. Let us assume that this current is I naught. We shall see what is I naught. Okay. So this becomes equal to, okay, Is exponential Vb by Vt is greater than I naught. So this is the condition of saturation for the NPN transistor. Just to differentiate between NPN and PNP, I will just make some modification. I will call this ISN, okay, which indicates that this is for the NPN transistor. Is for the NPN transistor. ISN exponential Vbe by Vt for the NPN transistor must be greater than I naught. All right. So I think we have to now look at what is the values of I naught, etc., okay, and come up with a condition, okay, for actual saturation of this transistor. So it will be in terms of the saturation currents and the betas of the individual transistors, okay, the NPN, PNP, etc., and the process engineer or the designer, okay, who is designing this, okay, must ensure that these conditions are satisfied, that is the betas of the transistors and the saturation current, Is values of these transistors, and only then the I squared L is going to function normally, okay, otherwise it is not going to operate. So, okay, so that is very important for the working of the cell. We shall take that up in the next class.